Good pre-calculus. I say morning because here I am drinking coffee and waiting on the sun to come up. Because yes, the sun is yet to come up. Been an early morning. Hope you're having a fantastic morning. When you see this, the sun will probably be up or it will be setting. But that's so. No matter what time of the day it is, it's a good time for pre-cal. Today we're going to be working. It's going to be a little bit of a longer lesson today, so let's jump right to it. The basic 8. I call them the big 8. Trig identities. An identity is something that will always be true for every value, for where your variable actually exists, for where it's defined. An identity is something that will always be true. For example, a squared plus b squared is a plus b times a minus b. This is called the difference of two squares. Hopefully that looks familiar. This is an identity because no matter what numbers I put into a and b, it's true. So if I put a 4 and a 9 here, then 2 plus 3 and 2 minus 3 would give me that. So on and so on. So that's what an identity is. It's a statement that's always true. It's an equation that will always be true, no matter what value you put in. Now there are a lot of identities that connect your trig functions. And what these identities do is they give us options for substituting one function for another function. It's kind of like if I give you an equation like this and I say a is 2, well then you can put a 2 here, a 2 here, and a 2 over here, so on and so on. That's what trig identities do, is they let us substitute one in for another. Alright, so the unit circle, remember this is radius of 1, you got a point x comma y. So we know that our sine values were y, because y divided by 1 is just y. Our cosine values are x, because x divided by 1 is just x. Tangent values are y over x. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. Okay, so the equation of this unit circle, you may remember this from geometry. If not, the equation for this circle, remember your center is 0, 0, so it's going to be x squared plus y squared equals, and then it's supposed to equal your radius squared, which our radius here is just 1, so 1 squared is 1. Now that's the equation of our unit circle. So there's some reciprocal identities here that I want to list out. Your reciprocal identities deal with cosecant, secant, and cotangent. I want you to think about this. If I say that sine is y, then for cosecant, couldn't I plug sine in for this y value and say that cosecant is the reciprocal of sine? So I could call cosecant 1 over sine of theta. If I know that sine of theta is y, and it says 1 over y, well, I can put sine of theta in here then, because that's what y is equal to. Same way for secant, I can do 1 over cosine. And for cotangent, now cotangent is something interesting. Cotangent is 1 over tangent. And I want you to write or, and we're going to fill this in here in just a second. 1 over tangent or, then you have your ratio identities. You've got tangent of theta is y over x. Y over x. Y over x. Watch what I'm doing here. Y over x. Y over x. Yeah, you see where I'm going with this. Sine of theta, your y value, over cosine of theta, your x value. So you remember that or thing I put down here? Or cotangent could be x over y, which is cosine theta over sine theta. Coffee break. It's good stuff. Okay, so a little bit about some trig identities. So we're actually going to use these a little bit later, and you'll see where in just a second. Keep going down here. All right, and it says note. Big old note here. Note. These single term identities can be squared to form new identities. In other words, if I was to square tangent, you know, anything I do to one side, I got to do to the other. So wouldn't tangent squared theta be sine squared theta over cosine squared theta? Remember that cosine squared and sine squared. Remember, you were squaring the actual sine and cosine, not the theta. Same thing over here. If I wanted to square cosecant and square this fraction, I can get cosecant squared theta is 1, which 1 squared is 1. That's why I'm just writing 1 here, over sine squared theta. So you can actually come up with new identities just by doing algebra to them. You can square them, you can do any kind of algebraic operation, and you can come up with a brand new set of identities. Okay, you remember that unit circle, or that equation for the unit circle? Well, the unit circle, if you'll remember, it was built with triangles, right? It was built with a 30, 60, 90 triangle. It was built with a 45. Matter of fact, you can see it right here through the back page of the paper. You got a triangle, right? A little triangle here. Well, if your circle was built by triangles, what do we usually associate with right triangles? The Pythagorean theorem, which is a squared. Do it this way. We got a little unit circle, right? Which is a squared plus b squared equals c squared. X squared plus y squared equals 1 squared, which is 1. You're telling me the Pythagorean theorem is how we write the equation for circles? That's insanity. We are using an equation for right triangles to come up with how we graph circles. That's just insane how math works. Okay, so there's these things called the Pythagorean identities. First one here, that's supposed to be a 1. If this is x squared and this is y squared, couldn't we replace that with cosine and sine? Because we know cosine is x and sine is y. So cosine squared x plus sine squared, cosine squared theta, I'm sorry, not x, plus sine squared x equals 1. Now let me explain the ramifications of this. If I get to a question and I see that the whole thing simplifies down to cosine squared plus sine squared, that means that whole thing is 1. Okay? Now there is a certain way that we like to write this. I'll tell you what that is here in just a second, just to make sure everything goes together. The second one here is what happens if I divide every term by cosine squared. Remember, I'm just doing algebra to it and making up new identities. What is going to happen if I divided every term, say we got cosine squared theta plus sine squared theta equals 1. What happens if we divide every term by cosine squared theta? You may be asking, why in the world would we do that? Well, what this allows us to do is to come up with new identities where we can simplify things in new ways. Okay, and I'm going to simplify that here in a second. Let's go to the third one here. Start with the same cosine squared theta plus sine squared theta equals 1. Notice how these all start with the same thing, cosine sine squared theta. Now, again, I know this may seem arbitrary for right now, but this is how we develop new properties and new identities. Okay, back up to the top here. The way that this is usually written is with sine first, just because sine is considered kind of like the godfather of the trig functions. You know, I get no respect. I'm going to make him an offer he can't refuse. That kind of guy. Sine is considered, I guess, like the godfather of trig functions. As a result, always try and write him first. It's just the way we've done things for years. Some guy way back before I was born decided it ought to be like that, so we're just going to, excuse me, reorder these two guys right here. Now these, let's see what these simplify to. What's cosine squared over cosine squared? Wasn't that just 1? Plus, what is sine over cosine again? If you look at the front page, y over x, sine over cosine, well that's tangent. Tangent squared theta. And 1 over cosine squared theta, 1 over cosine is secant, isn't it? See how this works? So we're going to be going back and forth between these functions. And then down here, we've got cosine over sine is cotangent, right? Sine over sine is 1, and 1 over sine is cosecant. Now, just because of the way that we write these again, somebody a long time ago decided that sine over sine ought to be first. So we're going to write it first. Sine over sine is 1. Plus cosine squared over sine squared, x over y, that's going to be cotangent squared theta is equal to, and then we've got, let's see if I can take this up, ooh, too much. And then we've got 1 over sine squared theta. Well, that's cosecant squared theta, right? So those are called your Pythagorean identities. Good old Pythagoras. Started with squares, then it got adapted for triangles, and now it's adapted for circles. That's just insane how that works. All right. Let's scooch you down a little bit. Okay, so it says, note, these identities can be solved for any term to form new identities. Coffee break. It's kind of like saying your Pythagorean theorem can be solved for A, B, or C, and you can come up with a new formula. Like A squared is C squared minus B squared, that kind of stuff. So for the first one, sine squared plus cosine squared theta equals 1. Let's say we solve for sine squared and we move the cosine over here. Just subtract cosine squared. Sine squared theta is 1 minus cosine squared theta. And then let's say we do the same thing with sine. Let's say we subtract sine over there, and we say that cosine squared theta is 1 minus sine squared theta. It's understandable, right? Let's do that with all of them here. Say we move that tangent over yonder, so that 1 is equal to secant squared theta minus tangent squared theta. Or say we move the 1 over yonder instead of tangent. Say we move the 1 over yonder. Say we got tangent squared theta. Yeah, I hear someone practicing out there. Distractions. equals secant squared theta minus 1. So it all started with those basic identities and just plugging stuff in, right? And then you've got 1, say we move the cotangent over, it's cosecant squared theta minus cotangent squared theta. Say we move the 1 over, cotangent squared theta equals cosecant squared theta minus 1. The whole point of showing you this is that these equations can be changed and moved around and solved and reordered to give you pretty much any order that you want. So this is kind of like a scavenger hunt at this point. Let me show you what I mean. So your basic 8, the big 8, right? You've got cosecant is 1 over sine theta. You've got secant is 1 over cosine. Cotangent is 1 over tangent. Tangent of theta is sine theta over cosine theta. Cotangent is cosine theta over sine theta. And then you've got your 3 Pythagoreans. You've got sine squared theta plus cosine squared theta equals 1. You've got 1 plus tan squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. Pause that real quick if you need to catch up on writing those. So again, these are your basic 8. I call them the big 8. All those other ones we found came from these guys right here. So here's what we're going to do. I'm going to show you how we're actually going to use these to make life super easy. It says use the basic 8 trig identities to simplify each of the following to a single trig function or number. See, here's the thing. Sine times cotangent can be, that one is okay. It's only 2 of them. It's a little easy. But that can be simplified quite a bit. Now, I can't simplify sine, so I'm just going to write sine of theta. But what could I change cotangent to? Now, here's where you got to be clever. I'm trying to cancel something out, right? The way that I do it at first is see if you can, obviously if you put 1 over tangent, I'm going to write it real lightly, that's not going to help. Because now you've got a fraction instead of a multiplication. That doesn't help. So let's go back. And what else is cotangent equal to? Well, instead of 1 over tangent, how about we try cosine over sine? You'll learn little tips and tricks along the way to help out with these, and I'll tell you about them here in just a second. So sine times cosine over sine. Won't these signs just cancel out if you're multiplying and dividing by the same thing? So that whole function just simplifies down to cosine of theta. That's why it's useful to know these things. It makes life easy for us. Now again, how I would have known not to use tangent, if I start with sine, or cosine for that matter, change everything to sines and cosines. The way I like to look at it is I want to get it to sines and cosines anyways. Now if this was a tangent, obviously that would be different because this isn't a tangent. But as long as you don't break any rules here, you could have changed that to tangent. And I'm going to show you what that's going to look like here. Keep in mind, I'm not making you do this again, but I just wanted to show you. If you change tangent or cotangent to tangent, it'd be sine of theta 1 over tangent theta, which is sine theta over tangent theta. But that didn't simplify anything very much. So I'd change that to sine theta over Tangent is sine over cosine. Then you'd have to multiply by cosine theta. And your sines would cancel out, leaving you with cosine theta. So, I mean, it's, oh man. Sometimes it's just easier to convert everything to sines and cosines. Sometimes it takes a little bit more work. Let's look at number 2. Sine squared theta over cosine theta times cosecant theta. Now that would be really annoying to try and plug in 3 different angles, one with a fraction, one squared, one multiplied together, and try and multiply those together by hand. Oh, so annoying. These are already in sine and cosine format, so I can't change those. But can I change cosecant to something? Sine squared theta over cosine theta times cosecant theta. I can change that to 1 over sine theta. Right? And now I'm multiplying by sine squared. Remember, this is sine theta times sine theta. And I'm dividing by sine theta. So won't that just divide out one of those sines? And what am I left with? Well, I've still got sine times 1, so that's going to be sine theta. On the bottom, I've still got cosine theta. Can I simplify that to anything? Is that one of my big 8? Can I simplify sine over cosine? Yeah, it's tangent, isn't it? If you like puzzles, this is probably one of my favorite sections that I teach, because I'm a big puzzle fan, and this is kind of like a big puzzle or a scavenger hunt or something like that. This is kind of along the same lines. So I really like these. Let's flip to the back. Coffee break. Never do pre-cal without your coffee. Okay. Cosecant squared x, 1 minus cosine squared x. See what kind of damage we can do here. Look at them individually. Cosecant squared x. Well, I could change that to 1 over sine pretty easy. So see what happens if we do that. 1 over sine squared x. And 1 minus cosine squared. Well, hang on a second. I did something about that back over here. 1 minus cosine squared was sine squared, wasn't it? So couldn't I just come over here and write sine squared x? Now think about this here. You're multiplying. This is over 1. So it's 1 times sine squared times 1. Isn't that sine squared over sine squared? Isn't that just 1? Huh. I'll be. And that's all from looking back to I saw that this wasn't one of my big 8, but it looks pretty close to something I've seen before. And it happens to be this guy right here. Well, fantastic. Let's keep going. All right, 4 sine x. 4 is sine x cosecant x minus cosecant x minus sine x. Now, I can convert this one to 1 over sine, but then I'll have sine times 1 over sine minus sine. So that's not going to work. So why don't we try, instead of converting like we did over here, why don't we try distributing this sine through? How about sine x times cosecant x minus sine squared x? Multiply that sine here and here. How about that? Okay, now let's convert some stuff. Sine x, 1 over sine x minus sine squared x. Well, what's sine x times 1 over sine x? That whole thing is just 1. 1 minus sine squared x. Wait a second. Get on back here. 1 minus sine squared is cosine squared. That whole thing simplifies down to cosine squared x. I'll be. That's crazy, isn't it? If you ever get stuck, go back and start over. There's nothing wrong with that. If you ever get stuck, go back and start over. Okay, now this one's actually a little bit interesting. You've got cotangent squared theta over 1 plus cosecant theta plus sine cosecant theta. Sine theta cosecant theta. Cotangent squared theta. The last thing I want to do is convert this to cosine over sine. I will if I have to, but if I don't have to, I don't want to. Okay, cosine squared or cotangent squared theta. Is there something else from over here that I could convert cotangent squared theta to? How about cosecant squared theta minus 1? Because what I don't want to do is change that to another fraction and have a fraction within a fraction. So how about I convert it to cosecant squared minus 1? Minus 1 over, mindful of my time here, 1 plus cosecant theta plus sine theta times 1 over sine theta. Well, that's all 1, right? So that's just going to be plus 1. Now here's the kicker. 1 plus cosecant theta. On the top, oh, I'm sorry, it's tilted. On the top, cosecant squared minus 1, that's a difference of 2 squares. That's a difference of 2 squares, isn't it? Remember that formula from the front? This guy? A squared minus b squared equals a plus b, a minus b. A squared, b squared. So if I factor that, I can get cosecant theta plus 1 times cosecant theta minus 1. That's where it gets weird. And then you've got, I'm going to try and hurry just for the sake of time. This will all go to cosecant theta minus 1 plus 1, which is just cosecant theta. Why not change that to 1 over sine? Because a fraction is more complicated than just actually saying what it is. I'm going to use that same rule over here, and I'm sorry, I do have to rush. I've got about 2 minutes left before this hits the no-go. I'm going to use this principle over here. This is a plus b and a minus b, isn't it? So won't that be sine squared theta minus 1? And sine squared theta minus 1, where am I at? Sine squared theta minus 1. Now notice how these two things are actually opposite here. That's actually going to be a negative. Let's say we take a negative out of there. Factor out a negative. It's actually going to be negative, and you've got a negative sine squared theta plus 1. That negative cosine squared theta. Pretty cool, isn't it? Alright, again, what I'm doing here is I'm taking and multiplying these through because there's nothing I can simplify right off the bat. I see that. And then I'm going to pull out a negative value here because there's nothing I can simplify here. So I'm just I'm guesstimating. I'm pulling out a negative value. And then lo and behold, 1 minus sine squared theta, cosine squared theta. Leave your negative outside, you're good to go.